Quadratic equations, factoring, level 9. Alright, in this video, we are going to go over an example where the coefficient of the linear term is negative, and that of the constant term is also negative. Keep in mind that whenever the coefficient of the constant term is negative, and granted that the quadratic equation is indeed factorable over the integers, then the signs of r and s will be distinct. One will be negative and one will be positive, regardless of the sign on the linear term. Alright, we will first solve the quadratic equation by trial and error. Solve the equation 6x squared minus x minus 2 equals 0. The first step is to always write the equation in standard form. Looking at the equation, we see that this step has been completed for us. Next, we need to find all the pair of factors of the quadratic coefficient a, in this case 6, and all the pair of factors of the constant c, in this case 2. The factors of 6 are 1 and 6, and 2 and 3, for a total of 2 pairs. Next, we find the factors of 2. They include 1 and 2, and those pretty much covers all of them, for a total of 1 pair. The factors we just found are potential values for p, q, r, and s. Next, we need to find all the possible factorizations with the given pairs. Remember that the signs for r and s have to be distinct. One has to be negative, and one has to be positive, because the sign on the constant term is negative. The fact that the constant term is negative means that we will have twice the amount of potential factorizations to test, because not only do we need to test each value for p, q, r, and s, we also need to switch the signs on the potential values of r and s. So keep this detail in mind. Let's first find the potential factorizations with the values of p and q represented by the pair 1 and 6, and the values of r and s represented by the pair 1 and 2. The first potential factorization is the quantity x plus 1 times the quantity 6x minus 2. The next factorization is obtained by keeping the values of p, q, r, and s in place, but with the signs on r and s switched, as follows. Remember, one has to be positive and one has to be negative, because the sign on the constant term c was negative. The next factorization is obtained by swapping the values of r and s in each grouping. Doing that, we obtain the quantity x plus 2 times the quantity 6x minus 1. Next, we keep the values of p, q, r, and s, and switch the signs of r and s. Doing that, we obtain the quantity x minus 2 times the quantity 6x plus 1. Next, we use the pair 2 and 3 to represent our p and q, and generate all the possible factorizations by using 1 and 2 as our r and s. We are essentially going to generate the same factorizations as the 4 previous ones, but this time around, the values of p and q are going to be represented by 2 and 3. Doing that, we obtain the quantity 2x plus 1 times the quantity 3x minus 2, the quantity 2x minus 1 times the quantity 3x plus 2, the quantity 2x plus 2 times the quantity 3x minus 1, and finally, the quantity 2x minus 2 times the quantity 3x plus 1. As you can see, the trial and error method can get pretty complicated really fast. Nevertheless, this method gets the job done. Next step is to find the sum of the products of the inner and outer terms. The first factorization, outer terms, gives us negative 2x, and the inner terms gives us 6x, and they add up to 4x. The second factorization, outer terms, gives us 2x, and the inner terms gives us negative 6x, and they add up to negative 4x. The third factorization, outer terms, gives us negative x, and the inner terms gives us 12x, and they add up to 11x. The fourth factorization, outer terms, gives us x, and the inner terms gives us negative 12x, and they add up to negative 11x. The fifth factorization, outer terms, gives us negative 4x, and the inner terms gives us 3x, and their sum is negative x. The sixth factorization, outer terms, gives us 4x, and the inner terms gives us negative 3x, and their sum is x. The seventh factorization, outer terms, gives us negative 2x, and the inner terms gives us 6x, and their sum is 4x. And finally, the last factorization, outer terms, gives us 2x, and the inner terms gives us negative 6x, and their sum is negative 4x. Having found the sum of the outer and inner products, we scan the list looking to match the linear term of the quadratic equation, in this case, negative x. We see that the factorization in the fifth row satisfies this requirement. So this quadratic equation is indeed factorable over the integers. It factors into the quantity 2x plus 1 times the quantity 3x minus 2. Next, we apply the zero product property to each factor and solve for x. Doing that, we obtain x equals negative 1/2 as one solution and x equals 2/3 as a second solution. Notice how the trial and error method can get really complicated, especially when you have a large number of potential factorizations that you need to test. This is the reason why I personally try to avoid this method and prefer using the method of decomposition and grouping. In addition, the only way you will find out if this quadratic equation is not factorable over the integers is by going through all possible factorizations. By using the second method, you can save precious time since you're required to test a smaller number of factors to determine if you can factor a quadratic equation over the integers. Let's go ahead and solve the same equation by using the method of decomposition and grouping. Solve the equation 6x squared minus x minus 2 equals 0. Alright, the first step is to take the coefficient of the quadratic term, a, in this case 6, and multiply it by the constant term, c, in this case negative 2. Doing that, we obtain 6 times negative 2, which is equal to negative 12. Next, we find the pair of factors whose product equals negative 12. Keep in mind that in order to obtain a negative number from a product of two numbers, one of the factors has to be positive and the other has to be negative. Let's first find the factors of 12. They include 1 and 12, 2 and 6, and lastly, 3 and 4. Next, we need to determine which factors will be negative. This is pretty easy. To determine this, all we need to do is look at the sign of the linear term. In this case, it's negative. This means that the largest factors have to be negative, because when we start finding the sum of each of the pairs, we want to obtain a negative expression. The only way that we can obtain a negative number is if the factor that is largest in magnitude is negative. So the factors on the right all need to be negative. This substantially reduces the number of factors we need to test, when compared to the trial and error method. Next, we find the sum of each pair. The first pair add up to negative 11, the second pair add up to negative 4, and the last pair add up to negative 1. And jackpot, we found the coefficient of the linear term, in this case, negative 1. We're going to use these factors to decompose the linear term in the next step. So using these factors, we go ahead and decompose the linear term, negative x, into 3x minus 4x. Notice that these terms add up to the linear term negative x. So all we did was to rewrite the equation. Next, we go ahead and create groupings. We always need to group a decomposed term with a non-decomposed term. So let's go ahead and group the quantity 6x squared plus 3x and the quantity negative 4x minus 2, making sure that we include a positive sign between the two groupings. It is key that you include a positive sign here. Some students forget to include the sign and get confused because the end result looks like multiplication. Or worse, they might think that the equation is in factored form. So make sure you include the positive sign. Once we create our groupings, we need to factor out the GCF from each grouping. For the first group, the GCF is 3x, so we factor that out and leave behind the quantity 2x plus 1. For the second grouping, the GCF is 2. But notice that in order to obtain a common binomial from both groupings, we also need to factor out a negative sign. So the GCF is actually negative 2. Factoring it out, we leave behind the quantity 2x plus 1. Notice that we ended up with a common binomial from both groupings. This is the end goal of this method. We want to obtain this common binomial so that we can factor it out. Doing that, we leave behind the expression 3x minus 2. Having successfully factored out the quadratic equation, we go ahead and apply the zero product property to each factor and solve for x. Doing that, we obtain x equals negative 1/2 as one solution and x equals 2/3 as a second solution. Notice how this method tends to be slightly faster than the trial and error method. From this point on, I will start factoring all quadratic equations using the method of decomposition and grouping. You are free to use any method you want. In an effort to save time, I will solve all quadratic equations solely by using this method. Let's go over an example where the quadratic equation is not factorable over the integers. Solve the equation 5x squared minus 5x minus 2 equals 0. The first step is to multiply the coefficient of the quadratic term, in this case 5, by the constant term, in this case negative 2. Multiplying the terms, we obtain negative 10. Next, we go ahead and find the pair of factors whose product yields negative 10. Notice that the largest factor has to be negative, so that the pair of factors add up to a negative expression. The factors of 10 are 1 and 10 and 2 and 5. In addition, the factor with the largest magnitude has to be negative, because the linear term of the quadratic equation is negative. Next, we find the sum of each pair. For the first pair, the factors add up to negative 9, and the second pair add up to negative 3. Next, we scan the sums looking to match the linear term, negative 5. Notice that it's nowhere to be found. When you exhausted all the possible factors, this is a telltale sign that you are dealing with a quadratic equation that is not factorable over the integers. In addition, we also see that the GCF of this quadratic equation is 1, so it's also a prime polynomial. This means that we can't solve this equation by factoring. We need to use other techniques to solve it. As you just saw, this method can streamline the process in determining if a quadratic equation is factorable over the integers. With the trial and error method, you need to test a larger number of factors. This is the reason I like this method. Alright, in the next video, I will wrap up factoring of quadratic equations by going over slightly more complicated examples.